Please observe. If you want to be a hero, please take a seat and learn. This is 740. Delete and earn. Okay, so you're given an integer array nums. Seems simple. You want to maximize the number of points you get by performing the following operation any number of times. All right, you're going to pick a number, nums I, for example, and you have to delete it to earn nums I points. Right, so you get the number of points corresponding to the number that exists at that index nums I. Afterwards, you must delete every element equal to nums I minus 1 and every element equals to num I plus 1. Right? So you get a certain number of points when you delete an element, but you also lose the opportunity to gain the points for the numbers that are 1 greater than that element and 1 less than that element. Return the maximum number of points you can earn by applying the above operation some number of times. Okay, so you can apply this operation any number of times. So when you have 3, 4, 2, for example, right? So for example, we have 3, 4, and 2. When you have 3, 4, and 2, well, you could delete this 3 and your score would increase by 3. But by doing that, you would have to delete everything that's 1 greater than 3. So you'd have to delete this 4. And you'd have to delete everything that's 1 less than 3. So you'd have to delete this 2. So the maximum score you could get is just 3. All right, let's try something else. Well, if we decided to delete and earn this 4, well, then we would get plus 4. And we'd have to delete everything that's 1 greater than 4. Well, there is nothing, right? Because the maximum element here is 4. And we have to delete everything that's 1 less than 4, which is 3. And there's 1, 3. So when you notice that, now there's a 2 remaining. So you can also add in this 2. So in total, you could get 6 using the solution, and you'll notice that if you also process 2 first and then 4, you'd get the same answer. Okay. So you get 6 here, right? And then this just walks through kind of how this works. So I'm not going to go through another example because I believe that, well, maybe let's go through this example because this example will better imply the nature of this problem and maybe an observation which will help us solve this more efficiently. Kind of a greedy aspect of this problem. There's not necessarily a greedy solution, but there's kind of a greedy aspect in terms of what you should do and when you should do it. Regardless, just walk through and then maybe what I'm saying will make a little bit more sense. Okay, so for this next example, we have repeated numbers, and the repeated numbers are what I want to articulate a point about. So we have 2, 2, 3 3s, and 1 4. Okay, so kind of the thing to notice here is when you delete a number, you end up having to delete all instances of a number greater than that, and all instances of a number 1 greater than that number, and all instances of a number 1 less than that number. So if you choose one of one number, you might as well choose all of that number, right? Meaning if you have more than 1 2 and you decide to delete and earn a 2, you might as well delete and earn all the 2s, because when you delete the first 2, it already deletes all the 3s and all the 1s. So the idea is, like, greedily, you might as well select all the 2s that exist if you're going to choose a 2, because that'll only increase your score, right? Because after I delete this 2, I'm going to have to delete these 3s. So I might as well select this other 2 because there's nothing else to delete. It'll only increase my score. So maybe the first observation is, well, the first observation is number 2 apparently because I'm foolish. Maybe keep track of the total score you'd get from deleting a number. Because that articulates what the total cost, what the total amount you'd gather. Because if you delete one of one number that exists, if that number exists more than once, right? If you delete 1 2, you might as well delete all the 2s, right? So this problem instead is a little bit different, right? You would think of it in its new form as saying, like, well, 2, if you use a 2, you'd get 4 points, right? Because there's 2 2s. If you use a 3, you get 9 points. And if you use a 4, you'd get 4 points. Right, so that means the problem's a little different, right? Because now if I use a 3, I'll get 9 points, but then I lose the opportunity to get 2s and 2s. Right, so for this problem, the optimal solution would actually be different because there's a different accumulation in terms of how many times each number exists, right? There's a different count associated. So there's a different score. Before, I only got 3 when I deleted 3, right? And I only got 4 when I deleted 4. I only got 2 when I deleted 2. But in this case, I actually get 9 points for deleting 3, and then I lose access to these, but that's greater than if I chose 2 or 4, because choosing 2, I'd get 4 points, but I'd have to delete this 9 points that I could potentially get, so I would get a total of 8, right? So in this example, it's actually better to delete a 3 to earn 3 points, and then notice all 2s and 4s are also deleted, so you might as well just keep choosing a 3 because you've already faced the consequences. So the basic idea is like, how do I articulate this in a way that makes sense? The only thing that popped in my mind is like, if you're doing something and you already got in trouble for it, you might as well just keep doing it if there's no further consequences, right? So if I delete a 3, the consequences, all the 2s and all the 4s go away. So there's no extra consequence if I keep selecting 3, so I might as well just select all the 3. So that's kind of the idea behind this approach. Not recommending that you go intentionally get in trouble or that you continue to do bad things if there's no further consequences. But I don't know. I'm wearing tie-dye today, so I guess I feel pretty cool. Anyways, so maybe what? So there seems to be kind of like a dynamic programming solution to this problem, right? Because like if I dealt with, I guess, any number, right? Like 2. Well, I'm going to get a score if I use the 2. And then the solution I would get is the best score if I use 4 onwards, plus the best score up to 1. What I'm basically saying is if I decide to use 2, or up to 0, I guess. If I decide to use 2, I can't use 3, and I can't use 1. Right? So if I use 2, I get that score, plus whatever the best score is I can get from 4 onwards, and the best score from 0 onwards. So it seems like dynamic programming, right? Like this idea of, well, the best thing I can get here is based off of what I could get doing something different. Yet it seems a bit problematic because there's no like sense of direction, right? When you run dynamic programming, you need information that's based off information that was already computed. But it seems like to find out what the best score is using 2, I need information about previous things and things that come after me. But things that come after me might be based on things that come before, right? So it's like I'm trying to base my best score on things that come after me, but things after me are going to be dependent on me. So like there's a strange cycle. If that doesn't make sense, basically it's hard to think about what the dynamic programming kind of recurrence relationship would be, because it seems like I can't use something one to my left and one to my right. So how do I like find an order of things that I should compute in order to, process this dynamic programming array and populate it? So I guess that might seem like your initial observation and think, okay, maybe it's not dynamic programming. Maybe it's like strictly greedy, or maybe I should sort and think about, something different. But I think what might be helpful in this example is to draw this system as a graph, and then from there decide if it is or it isn't something that can be solved by dynamic programming, right? So when we talk about what you can do at any situation, right? Well, let's look at a system like this, for example. Okay, so 1, 2, 3, 4, 5, and 6. And then let's say there's the score of using this system. So that would mean how many times that number existed. So imagine our example was 1, 1, 2, 3, 3, 3, 4, 5, 6. So the score you would get, where you'd get 2 1s. So basically saying this is an example problem to kind of give us an intuitive understanding of how this works. Let's model this system as a graph where each number gets its own node, and then the score is underneath. So 1 would get 2 points because there's 2 1s. So in total, you would get 2 points if you decided to use the 1. 2 would give you also 2 points because there's only 1 2. 3 would give you 9 points. 4 would give you 4 points. 5 would give you 5 points. And 6 would give you 6 points. Okay. Now, let's just start in the center here. If I wanted to use a 4, what would that mean? Well, that would mean that I can't use, or let's actually start at the beginning and see if this makes sense processing it. If I want to use a 1, then I can't use a 2, right? So if I want to use a 1, I can't use a 2, so the next path I could take is 3. If I wanted to use a 2, I can't use a 1, right? And I can't use a 3, right? Because like if I want to use a 2, the 2 things beside me get deleted. So what I'm basically saying is I have an edge to the path that I could use if I decide to use myself. If I decide to use a 1, there's no way that I can use a 2. So I'm kind of encapsulating that idea by using a graph where the edges are the connections between nodes that you could use together, right? I could add the score of using a 1 and the score of using a 3 together, because if I delete and earn a 1, that only deletes the 2. I can still use the 3 subsequently, okay? So if I want to use a 2, I can't use a 1 or a 3, but I can use a 4. If I want to use a 3, well, I can't use a 2 or a 4, but I could use a 1 and a 5, right? So I guess you could say, well, I could draw another link from 1 to 3, but that idea is kind of already encapsulated here, right? I've already encapsulated the idea, right? Because the problem with our dynamic programming solution was, well, we can't find this, we can't have this idea where there's a cycle, right? Because using dynamic programming, I have to have some base thing that I solve first. So if I don't have a base thing, a base case that I solve first, I'm never going to be able to build this catch. But you could just argue that, well, I've already populated 1 to 3. I already have dealt with this constraint, right? If I use 1, then I can use 3. And if I use 3, I can use 1. But I don't need to state that twice. If anything, that's just kind of redundant information. So I guess the next thing that 3 could use is 5, right? And 4, I'd play the same game. Well, 4 can go to 2, but 2 is already pointing at 4. And 4 can't use 3 or 5, so the next thing 4 could use is 6. The next thing 5 could use is, well, nothing. And the next thing 6 could use is, well, nothing again, because we already have edges coming from the other side articulated at that point. Now, this system, on the other hand, can be solved with dynamic programming, right? Because, well, this is an obvious DAG, right? I can solve this subproblem, and then this subproblem, and this subproblem, and this subproblem, and this subproblem, and this subproblem, right? But what would that problem be? Because there's only one link going to each thing. So this doesn't actually encapsulate the whole idea, right? Because, well, what's the best score I could get with the number 3? Now, this is where it gets kind of weird, right? The best score I could get using 3, or involving 3. Either I use 3 or I don't use 3, okay? The best score I could get, let's call it the best score up to 3. So the best score I could get up to 3 is either the case where I decide not to use 3, so that would be the maximum of the case where I decide to not use 3, so that would be the best score I could get up to 2. Or if I decide to use 3, what would that mean? Well, then I would get the score associated with using 3. And up to this point, all I could use is the best score up to 1. So this is basically just articulating, this is if I don't use 3, what's the score, the best score I could get up to 3? And this is if I do use 3. So this becomes down to one of those like kind of intuitive things you have to recognize, which is sometimes when you're dealing with dynamic programming problems, you can ask yourself the question, either I can do something or I can't do something, right? And that will lead you to the recurrence relationship, right? In this problem, either I can use a number or I don't use a number. So my score is going to be the maximum of either of those, one of those choices, right? It's the maximum of either, well, I decide not to use 3, so that means I get to use 2 and the best thing up to 2, or I decide that I am going to use 3, so that means I get the score associated with 3, but now I no longer get to use 2, so I can get the best score up to 1. So if we just look at the range of numbers that could possibly exist, and we walk through each number, because the problem is for this problem, well, is like, it's not necessarily that we have all the numbers in the range, right? It could be the case, well, it goes like 1, 2, 5, 6, 7, or something like that. So if you drew this as a system, right, the problem is that for this case, you know, you want the best score up to, you don't want to connect these two to each other because they're not 1 or 2 away, right? Because since we're dealing with values, we don't want to look at the values of the nodes. We want to look at all the values in the system to make a decision. Hopefully that makes sense. I'm trying to think of a better way to articulate that, right? Because like 2 and 5 can connect to each other because they're more than 2 away from each other, right? So it doesn't always take this structure. Instead, what happens is we can think of it in terms of this structure. If we had 1, 2, 5, 6, and 7, we could think of it like this. You know, we could draw our initial nodes. You know, our initial nodes. So I'm trying to think about making this clear because I'm going to make a thumbnail at some point, and I'm guessing that this will be the point where I do. You know, I can draw the initial nodes. Because what I want is I want it to have this form so I can run this recurrence relationship saying, well, the max thing I can have is the best score up to not using me, right? You up to 2 for 3. The best thing I could get up to 2. Or I can use 3 and use what connects to 3. Okay, so how would I do that where they aren't continuous, right? It doesn't go in order, not in order, but where it doesn't have all the numbers in the range, right? This has all numbers in range from 1 to 6, so this is very clear. But this doesn't, right? There's a hole in the middle. It's missing 3 and 4. So what you can do instead is, well, you can draw those numbers out. Right? And then you can put these dummy nodes in the middle. 3 and 4, and somehow I messed that up. But there you go. So like this, and then you can just articulate the score of these nodes that don't really exist that we're just putting in for filler, right? We can say the score of these nodes is what? Well, the score of this exists. This is 2. The score of this 3, well, this 3 is not even in your initial array, so let's score 0. The score of this 4 is 0. The score of this 5 is 5 and 6 and 7. So now you basically have it in the form where you can use that recurrence relationship because you're just looking at the best score of the num that comes before it, right? So now you can do this rigmarole again. Right, so now you can have that form again with your system. So I guess essentially our recurrence relationship is the best node score for something like this is, well, the best score for the number num is the best score of either you don't use the num, so it's the num that comes before it, right? It could be a num that doesn't actually exist in your normal array, but you'll keep track of what the total score is up to that, so you can keep this form. Or you get the score if you use the num, plus the best score if up to the number -2, because you can't use the previous number anymore because you decided to delete and earn the current number you're looking at. So this is the recurrence relationship. So essentially what we have to do in summary is, well, we'll find the total score you'll get for each number, and then we'll run a loop through all the possible values to populate what the total best score is we can get. All right. And we've done that by first noticing that even though it seems like there's like 2 directions and we won't be able to use dynamic programming, if you actually model the problem appropriately in a graph, you'll recognize that it is solvable using dynamic programming. And that's through the observation of saying, I'm going to use something or I'm not going to use something, and corresponding that to the graph. All right. So the first thing we'll do is we'll find out the total score that we can get from each number. And we're going to need to find eventually the best score, so might as well kill 2 birds with 1 stone by drawing out both of those here. All right. And then what we're going to do is we're going to populate the score we get for each number. So we look at each num in nums, And we're going to say, okay, the score we get for that num, we're going to add equal the num, right? So if you see the same num 4 times, then you're going to add up that number 4 times, and that'll give you that score. And then, well, we need to look at all the numbers in the range from the minimum number to the maximum number, right? So we could say, well, for num in range, the minimum of nums, all the way to the maximum of nums, plus 1, right? Because we want to get all the numbers in the range, right? We looked at the minimum number 1 and up to 6, right? When it was 1 through 7, we have to start with the minimum number all the way to the maximum number to make the decision about what we can delete and what we can earn. Of course, there's some dummy variables where if we delete them, we earn nothing. So all it does is service building this graph, right? And you might say, well, doesn't that affect our runtime? Well, you'll notice here that, you know, the nums length is 2 times 10 to the 4, and nums of I, each element is only up to 10 to the 4. So this range won't exceed the length of nums, right? Because there's only 10 to the 4 options. So I guess the only problem is if you had a small input, right? If it was only like 3 elements in nums, it's going to end up going through all 10 to the 4 options, right? That could happen. But it's still, in terms of runtime complexity, which we ultimately care about, which is kind of aggravating sometimes as a side note, because sometimes the most time efficient thing in terms of big O notation, time complexity, space complexity, isn't in reality what would best service what you're trying to do. But in terms of Leetcode and data structures and algorithms, this is the most time efficient approach, I suppose. Okay. Or more, maybe there's, I haven't looked at the discussion yet, so maybe somebody far more intelligent than me discovered, you know, an even faster solution with less space utilization or whatever, but not me. Okay, so now we can just play this recurrence relationship game, right? So the best score I can get up to this number is, well, either I don't include this number in my score, right? I don't delete and earn this number, so I can figure out, I can use whatever the best score is to the previous number. So it's either that, or I use this number, so whatever the score is I get from this number, plus the best score up to this number minus 2. Since I've decided to use this number, I can't use the previous number that's 1 lower. And at the end, I just figure out, well, what's the best score at the max of nums, right? Because that'll give you the best score up until the end, which is the best score total in the system. So this is technically, look at that. It's a 4-line solution. So what is the time and space of this? Let's call n the length of nums. And we'll notice that n is greater than or equal to the max num and the min num. All right. So we'll just call it n. Okay. And then for time, well, we have to look at all numbers to find out the score we get for each number, right? So we have to look at all n numbers, and then we have to look at the range from the min num to the max num, but this is always less than n. So in terms of the worst case scenario, this statement will always take longer than this statement, because this statement is at most n, right? So this is n, and this is at most n. So, and for each of that most n things, you do something constant. So you're doing at most n things, or 2n things, but in terms of runtime complexity, that would be O of n. In terms of space, well, we have to create this default dict and this default dict. Every number gets a score populated to it, right? And it's possible that your entire array is unique. So every single number is unique. So you're going to use O to the n space, at least, right? But then also for here, you have to populate the best score for each number in that range. So, but that could again be at most n. So this is again at most n, since this loop can never be larger than n itself, since we're looking at the constraints where the number itself is always less than 2 to the 10 times 4, which is less than num.length. So then again, it's just rows with n. Hopefully that makes a little bit of sense. It's kind of all over the place, but hey, what are you going to do? All right. Have a good rest of your evening, day, morning, afternoon, whatever's going on with you guys. Peace out.